Okay, so let's have a very quick reminder of what specific heat capacity is and how we might go about calculating it. So what I'd like you to imagine is a block of metal. So I'll just draw that as a block like this. And if you remember, the specific heat capacity is a very particular thing. It's the number of joules of energy you need to raise 1 kilogram of material by 1 degree C. So here's my block of metal, and let's imagine that this is 2 kilograms. So we add some heat energy to it. So we might use an electrical heater or something like that, which lets us know how much heat we've put in. And let's say that we've fed in 10,000 joules of energy, so 10 kilojoules, but we've got to work in regular joules. And we know what that's going to do is it's going to raise the temperature. Maybe it was at room temperature to start with, 20 degrees C, and it went up to 30 degrees C. So you'll notice that's a temperature change of 10 degrees C. So what would you do to work out the specific heat capacity of this material? Well, we use the letter C for specific heat capacity, but I'm just going to write SHC here just to make it clear what we're trying to achieve. Okay, but it would actually be what is C? Well, we know that's the number of joules needed per kilogram per degree C. Well, we've not done 1 degree C, we've done 10 degrees C. So for 1 degree C, we'd need a tenth of this number. We'd only need 1,000 joules. But we've raised 2 kilograms. So we've used 1,000 joules to raise 2 kilograms by 1 degree C. So we would only need 500 joules to raise 1 kilogram by 1 degree C. Okay, so what I'd like to do now is to go into the laboratory and to show you an experiment that we can do to measure the specific heat capacity of a metal block. But just before we rush off and do our experiment, I think it would be a good idea for me to remind you of what the formula is for specific heat capacity. What you'll notice here is that the energy we feed in, the 10,000 joules, came from the mass 2 times by the specific heat capacity, which was 500 C, times by the change in temperature, which was 10 degrees C. Now this is tricky. Change in physics, we use the symbol delta, okay? And then what do we use for temperature? Well, either capital T or most of the specifications at the moment use theta. So the formula there for specific heat capacity, the energy we would feed in is equal to the mass times by the specific heat capacity times by the temperature change. But today what we're trying to do is we're trying to determine the specific heat capacity. So remember, you need to be able to rearrange this for C is equal to, so we're going to divide by M and we're going to divide by delta theta. So the specific heat capacity is E, the energy we feed in, divided by the mass multiplied by the temperature change. So we'll very quickly look at the apparatus that we need to do this experiment. I've got my aluminium block here. It's been cut out of a long bar of aluminium, and you'll notice it's got 2 holes in the top, and one of those holes is going to hold the electrical heater, and I'll push that fully in a minute, and the other hole is going to be used to measure the temperature of the block at the beginning and at the end, because it's going to be heated by this heater. We need the mass of the block, so I've got some scales here. And to work out the power, we need a voltmeter, an ammeter, and a stop clock. And finally, we need a source of power. So we've got our lab power supply. And just for safety, I've got a heat-proof mat here because this is going to get quite hot. So I'm going to go back to the board now, and draw the apparatus and how we set it up, and then we'll come back to the lab and we'll do our experiment. So now you've seen the apparatus we're going to use, let me just draw it on the board and show you what data we've got to collect. So we're going to use our aluminium block. So I'll just draw the block. And if you remember, the block's got two holes drilled in it, one for the heater and one for the thermometer. So here's our block, and I'll make sure I leave a hole for the thermometer and a hole for the heater. Now, when we do this experiment and when I draw it, I'm going to make a few mistakes, I call them. I'm going to do a few things that aren't quite right. But I'm doing that very intentionally because there is going to be some experimental error here. And at the end of the experiment, we'll discuss what we could have done to get a more accurate result. So there's our block, and we know that that's aluminium. We could use any metal, and in the class, we have a range of different metals. So you can do aluminium, or you can do copper. I think we've got some steel as well. So let's get our thermometer. So our thermometer is going to sit here. There it is, and come out of the block. And hopefully we'll be able to read it without taking it out of the block, but let's see how we get on. Okay, and then the heater, this is the tricky bit, okay, because it's an electrical heater. And what we're going to do with the electrical heater is we're going to work out how many joules per second go into the electrical heater. So it's a little immersion heater like that, okay, and it's going to have two wires coming out of it, and we're going to connect those to a power supply. But this is the tricky bit. We need to work out how much energy that heater gives out. So if we know how much electrical energy goes in, then we can work out how much heat energy the heater gives out, because we're going to assume it's 100% efficient, that all the electrical energy goes to heat. So we need some kind of a power supply. I'm going to draw the power supply just like that. Okay, we're not going to use batteries. We're going to use a lab power supply that's connected into the mains and then produces a DC voltage. And we'll connect up to the heater. So here we go. It does take a while to draw these, but I'm keen that you see it being done sort of in front of you, as it were. So that's one connection. And here's the second one. But to work out the power, the electrical power, we need to know how much current flows into the heater. And we also need to know the potential difference, the voltage across the heater. So there's how we measure the current with our ammeter, and we'll put a voltmeter across the heater. There we go. And we'll do it in a second, but if we multiply the potential difference by the current, the volts by the amps, okay, that will give us the number of joules per second. So we clearly need one other thing to work out how many joules put in total. We need a stopwatch or stop clock. So I'll just draw something like that to indicate the stop clock. Okay, so we've got all the bits of equipment we need there, bar one thing. Yep, we need to know the mass of the aluminium block. So we've also got to have some way of weighing the block. So we're going to put the block on scales. Okay, and I'm not suggesting that the block is going to have a mass of 936 grams. I'm just pointing out that these are scales. This is a stopwatch or stop clock. I'll put stop clock. Okay, we've got our ammeter, our voltmeter, thermometer, and the heater. So what we need to do now is work out what measurements do we need to make. Okay, so you've got the apparatus there. So let's just remind ourselves, we're trying to find the specific heat capacity, and we know that the energy we feed in is equal to the mass times the specific heat capacity times the change in temperature, delta theta. We're trying to find the specific heat capacity. So the specific heat capacity will be the energy we feed in, and I'll show you how to work that out in a minute, divided by the mass, which is on the scales, and also divided by the temperature change, which we can get from the thermometer by measuring the temperature at the start of the experiment and measuring the temperature at the end of the experiment. So this is the formula we're going to use. And the reason I put that formula up is we are going to need to work out the energy fed in, the mass of the block, and the temperature change. So I'm going to write down a sort of table here of the data that we need to take. Right, so this is a bit of a long list, so bear with me here. The first thing we're going to need to measure about the block is we're going to need to measure the mass of the block. Okay, so I'm going to write here mass. Get a slightly better pen. Mass equals. Now, we're going to have to measure the mass in the correct units, so we're going to measure the mass in kilograms. Okay, now I've written that in green because that's a number that we need here. Okay, right, the next thing we need to do is measure the temperature at the start of the experiment. So it's the start temp. And that will be a value in degrees C. Then we'll run our experiment for a known amount of time and we'll find the finishing or the end temperature. And that will also be in degrees C. But I'm going to switch to my green pen. We need the change in temperature, so the temp change. And that will be also in degrees C. Okay, so now the tricky bit is how do we work out how much energy have we put into the block? So we'll do that next. Right, this is quite synoptic. It's going to bring all our ideas together. We need to work out how much energy we're going to put in. Now, there is a quick way of doing it. Energy is power times by time, so joules per second times by time. And on these heaters, they often write on them what the heater's power is if you connect it to the right voltage. But we're not going to rely on that, and I'm not sure the heater I've got's marked. So we're going to do it using our voltmeter and our ammeter and our stopwatch. So the first thing we're going to measure is the potential difference. And we're going to try and keep that constant whilst we do the experiment. So the potential difference in voltage, probably around 12, 13, 14, 15 volts. We're going to measure the current that flows into the heater, and that's going to be in amps. Okay. Now, you might remember that power, the number of joules delivered every second to the heater, is potential difference times current, or volts times amps. So if we times those two together, we will get the power. So we'll work that out, and that will be in watts. I'm going to write after that joules per second because it's a nice way to think about it. Okay. We're going to time the experiment. And the time, I'm going to do it for 10 minutes, okay? Now, let's not fall into the trap of minutes. We're doing the power in joules per second. So if we do the time in minutes, we need to convert it to seconds. We'll do 10 minutes. So 10 minutes will be 600 seconds. And finally, I'm going to switch to the green pen again. The energy that we feed in to heat the block is the power times by the time. So we'll have a value here of the number of joules that we fed in total to heat the block. So if you look at the formula now, we've got the energy we fed in, yep, we've got the change in temperature, and we've got the mass, so we can then calculate the specific heat capacity of the metal block. So let's head off into the lab now and do our experiment, and then we're going to come back to the board, put our numbers in here and see if we can calculate from our experimental data the specific heat capacity of our aluminium block. Okay, so let's get set up. So the first thing we need to do is measure the mass of the block. So I'm going to check that the scales are zeroed and put the block on gently. Now, normally for GCSE, we consider this to be exactly a kilogram, but let's do it properly today. The mass of the block, so I'm going to write that down, the mass is equal to 988 grams, 988 grams. And I'll write that on the board in a minute. So we've got the mass of the block, so I'll just put the scales out of the way. And now let's put all the apparatus together. So here's our electrical heater, and it's a fairly tight fit inside the block, so that fits well. And we'll wire that up to our power supply. So it's DC heater, so we're going to come out of the DC into our ammeter. The ammeter's probably going to read minus if I do it that way around, but it doesn't matter. Okay, out to the other side of the ammeter and into the block, and then back to the power supply. So there we go. So we can measure the current through the heater. So if we switched on now, that would start to warm up. But we need to measure the potential difference across the heater. So I've got a voltmeter here, and I'll plug that in. And that goes in here. And the other connection, maybe I should have used a red lead, but it doesn't matter what colour the insulation is. Connect that in there. Okay. So we've got everything now set up. So we've got one more measurement to make before we switch on, the starting temperature of the block. Now this block's been sitting in the room for quite a while, so it's at room temperature. But just to be sure, I'll leave it for a few moments. Very quickly talk to you about health and safety. Okay. Firstly, the block is going to get very warm, so we have to be careful that we don't burn ourselves on the block. And I've put it on a heat-proof mat to get it off the surface of these wax desks. The second thing is it's an experiment where you can't you have to leave it for a while whilst you're waiting for the temperature to rise. And you can't then go off and run around the laboratory. The common thing is to catch this with your arm, particularly when you have longer thermometers, and to break the thermometer off. And then you're in the realms of broken glass and things like that. Okay, so you obviously have got a trip hazard if you've got electrical cables over here running off the edge of the desk, etc. So those are comments you could make on health and safety. So let's have a quick look at the starting temperature. It's quite cool in here today. So I've got, and I should get close, and I should get at 90 degrees to the thermometer. So I've got a starting temperature at the start of 18 degrees centigrade. So we're ready to switch on the power supply and start our experiment. So we've got everything set up. We've got the mass of the block and we've got the starting temperature. I've dialed up about 12 volts on the power supply. I have just turned this ammeter around so it's reading a positive number, though that doesn't make a difference. So let's turn on, and the moment we turn on, I'm going to start the stopwatch. So 3, 2, 1, go. Okay. And the stopwatch is ticking away. We're going to wait for 10 minutes and we're going to see what the temperature rise is, in other words, what the final temperature is minus the starting temperature after 10 minutes, 600 seconds. But whilst we're doing that and whilst we're waiting, because we need to work out the power of the heater, the number of joules per second going into the heater, we need a value of the potential difference, the voltage and the current. So we've got those on these two ammeters. So 12 volts, 12.0 volts, and we'll go for 4.5 amps. So I'll see you in 10 minutes' time. So we've got about 10 seconds left before we've run for 10 minutes, and the block's been heating up during all of that time. So I'll turn the stopwatch around. Not sure if you can see that on the camera, but there we go. And that's 10 minutes. And we've got a finishing temperature of 45 degrees C. So I'm going to make a note of that. 45 degrees C. Okay, so I'll turn the power supply off. One or two people might be screaming at the screen and saying, FJ, what are you doing? I have made a few minor, I wouldn't say mistakes, but I've done some things not quite right on purpose here. But I've done that purposefully, so when we analyse our data and get our result, it won't be quite right. And then we can discuss the areas where we could have improved the experiment to get a more accurate result for the specific heat capacity of aluminium metal. So let's now put the numbers in that we got from our experiment. So the mass of the block was 988 grams, so we've got to be a bit careful, 0.998 kilograms. We knew the starting temperature was 18 degrees C, and our finishing temperature was 45 degrees C. So that gives us a temperature change of 27 degrees C. And then all of our meters, so we had a voltage of 12 volts. It was 12.0, so perhaps we could do that. Okay, we had a current of, quite a large current, 4.5 amps. And to work out the power, it's potential difference times current in joules per second, so that's 54 watts. So it was probably a 50 watt heater, and we had it turned up just a tiny bit higher. And finally, the energy we've put in is 54 joules per second times by 600 seconds. So the energy we put in was 32,400 joules, or 32.4 kilojoules. So what we'll do now is we'll see if we can use those numbers to determine the specific heat capacity of our aluminium block. So let's calculate the specific heat capacity, and you might have noticed I made a mistake there, not 998 grams but 988 grams, so 0.988 kilograms. We got that right because we measured that on our scales earlier on. So here we go. To measure the specific heat capacity experimentally, the specific heat capacity of our aluminium block, okay, will be the energy we fed in, which was 32,400 joules, divided by the mass of the block, get it right this time, 0.988 kilograms, times by the temperature change, or the temperature rise, 27. Okay, and if you bash all that out on your calculator, you get a specific heat capacity of 1,215 or thereabouts joules needed to raise 1 kilogram by 1 degree C. Okay, well, that's our experimental value. We can head over to the internet or a data book for one that's been done in really good laboratory conditions by seriously good scientists. And the specific heat capacity for aluminium that's given in data books or on the internet is equal to 897 joules per kilogram for every degree C temperature rise. Okay, so you may be thinking, oh, this is dreadful. We've made a hideous mistake. Well, yeah, we're about 35% difference between the data book value and the value in the lab, but that's fine. And what I'm going to do next briefly is just talk to you about why our number is okay, and particularly why our number is higher than the agreed data book value. So why is our number so far out? And I'll tell you a little story actually very quickly. When I did the calculation a few minutes ago, I got ours coming out as about 500 joules per kilogram per degree C. And I was like, hang on. Firstly, I know I've made a mistake with the maths. But secondly, there is no way that the number that we get in the lab, unless we're completely mad, okay, is going to be lower than the data book value. So what it says is that special scientists and good scientists need 897 joules to raise a kilogram by 1 degree C. And we needed, at school, we needed 1,215 joules to raise 1 kilogram by 1 degree C. So why do we need more? Well, it's not the precision of the meters or anything like that. Here's the problem. And maybe you were shouting at it, at the screen at me to try and correct me. We heated up the block like this. So what's happening? To begin with, all of the heat is going into the heater to just warm the heater. None of that energy that we put in is going into the block. And then this is really nice and warm. And then later on, some of the heat is going into the aluminium block, which is great. And we're heading off to this number. But I can even feel it radiating now. A lot of that heat that we put in and that we calculate that we've put in is being radiated to the atmosphere. So what we should do to improve this experiment, and I think most people on YouTube show it this way, is we should lag the block. So I'm going to put the block inside a plastic beaker, which is a bad conductor of heat, and I'm going to wrap it tightly in cotton wool, and I should really put a lid on it. This is a calorimeter, a thing that will keep the energy inside the block. Now, if we'd done the experiment like that, we would have got a value still larger, but much closer to this value. So that's another improvement that you can do with this experiment. And that's a really good way to fairly simply or quickly in the lab measure the specific heat capacity of a metal block. Now, there is another way to determine the specific heat capacity of a material, and this second method uses a graphical method. It's not at all easy, so you'll have to bear with me on this. It's quite difficult, and I think it verges into the realms of A-level, but it is mentioned in the GCSE, so let's go through it very quickly. So what I didn't tell you was, when I was doing the experiment that I've shown you already to determine the specific heat capacity of the aluminium, I actually took a measurement of the temperature of the metal block every minute. And I didn't do it for the whole 10 minutes, but I did it for 8 minutes. So this table you've got in front of you here is the data that I gathered. So it was at 18 degrees C at the start of the experiment, and then after 8 minutes, it was at 38 degrees C. So I'm going to show you now how we can plot a graph of this and use that data to determine the specific heat capacity graphically. So what I've done here is I've plotted a graph of the data I got for the experiment, and you'll see I've put time along the x-axis. So I've done it in minutes, 1, 2, 3, 4, 5, 6, 7, 8 minutes to make it easy. And I've done the temperature on the y-axis, and then you'll see the green points I've plotted. The green points are the temperature at the start, 1 minute, 2 minutes, 3 minutes. And then I've done a line of best fit as best I can. Okay. And then what I've done is I've worked out how much did the temperature change using the line, so that avoids this sort of scatter of points, you know, and experimental error. So the change in temperature on the line was from 18 degrees C to 37. That was in our 8 minutes. So that's 19 degrees C temperature change. And we went from 0 to 8 minutes. And I've got to be careful to say that that is 480 seconds. So we're going to use those two numbers to determine the specific heat capacity of the aluminium. Okay, so let's see if we can explain how we do the specific heat capacity with the numbers we got from the graph. So you remember that the formula for specific heat capacity is E equals mc delta theta. So the energy fed in is equal to the mass times the specific heat capacity times the temperature change. We need the specific heat capacity, so let's rearrange for specific heat capacity. C is equal to E over m delta theta, so that's rearranging that. And we know a few things. We know the energy fed in is the power, the number of joules per second, times the number of seconds we did it for. So our heater, we worked out from the previous experiment, was the potential difference times by the current, and that gave us 54 joules per second. It was a 54 watt heater. Okay, and on our graph, I left it going for 480 seconds. Okay, so the energy that we feed in is the power times by the time. So this energy here is the power times by the time. So the specific heat capacity will be the power, the number of joules per second, times by the number of seconds we left it running for, which is what we showed on our graph, our 8 minutes, divided by the mass of the block, 0.988 kilograms, multiplied by the temperature rise that we had on the graph, the delta theta, and that was 19 degrees centigrade. Bash all that out in your calculator and you get a specific heat capacity of 1,381 joules needed to raise 1 kilogram by 1 degrees C. So think about what we did there. We got all the numbers from our experiment and then we used those numbers to plot a graph. Now, this number is still way too big compared to the data book value of just under 900 joules per kilogram per degree C. But of course, in an exam, you can comment on why the data book value is so much lower. Do you remember we had so many losses to the environment? We didn't have the block wrapped up, lagged very well. So an awful lot of the heat energy that we were feeding into the block was not warming it up. It was disappearing out and just warming up my laboratory. So I do hope you enjoyed that experiment and you feel you've now got a really good understanding of how to determine the specific heat capacity of a metal and all the things that we did wrong that we should improve. Also, if you were going to do a liquid, it wouldn't be that different. You'd put the liquid in a beaker that was heavily lagged as well, and you'd make sure that you stirred it. Anyway, I hope you feel confident now, and best of luck with your required practical questions in any exams you might have in the future.